So let's get started with the math calculation portion of the aggregate properties. The first one we're going to cover is the coarse aggregate angularity. At the top of the page, you'll see a value for the %1 fractured and %2 fractured faces. The formula for this calculation is at the top of the page. So let's cover the % fractured one face. F representing the total mass of particles with at least one fractured face, and N representing mass of uncrushed particles. Plug your numbers into the formula. So the top portion of the formula, F 375, I'm going to divide that by F plus N, which will give us 390. 375 divided by 390 gives us a 0.9615, and you times that by 100, which yields you a 96.2. Rounded to the nearest whole number, 96 is one fractured face. The second portion of this equation is determining the amount of two fractured faces. Same formula, different values. 360 mass particles with at least two fractured faces. 30 is the mass of particles with less than two fractured faces. So 360, you would divide that by plus F plus N, which is 360 divided into 390, which yields you a 0.9230 times 100. Round that to the nearest whole number, which is a 92. We will now calculate the sand equivalent value of the B sand. At the top of the page, you will see the formula. Your sand divided by your clay times 100 equals your sand equivalency value. On this product, we ran test 1, test 2, and test 3. Get your sand value, 3.4, divide it by your clay value of 3.7 times 100. Gives you a 91.9. Your second test 2, sand value of 3.1, divide that by your clay value of 3.3, yields you a 93.9. Test 3, sand value of 3.3 divided by your clay value of 3.6 yields you a 91.7. It's very important how we round these numbers. On test 1 is a 91.9. You round that to a 92. Test 2 is a 93.9. You round that to the 94. Test 3 is a 91.7. We're going to round that to a 92. Very, very important. No matter the numerical value to the right of the decimal, you always round to the next highest whole number. So let's say test 1 was a 91.1. It's a 92. You round to a 92. Let's say test 2 was a 93.4. Always round to the next highest whole number. This is the only math equation in this class where this type of rounding applies. We ran 3 tests, 1, 2, and 3. We got our individual result for each test. Now we need to average those 3. You add 92, 94, and 92, yields you a 278. Divide by 3, gives you a 92.7, and always round to the next highest whole number, so your answer would be 93. So now we will move to our second fine aggregate of this blend and calculate sand equivalency, which is the natural sand. Again, same math. Test number 1, our sand value was 3.5. Divide that into 4.5, which is a clay value, yields you a 77.8. Round that to the next highest whole number, which is a 78. Test number 2, our sand value is 3.7. Divided into clay value of 4.6, which yields us an 80.4. Here's a good example of rounding to the next highest whole number. That 80.4 now becomes an 81. Test number 3, Our sand value of 3.6 divided into the clay value of 4.6 yields us a 78.3. Rounding that to the next highest whole number is a 79. The individual results of those three tests, we need to add those three, divide by 3, so 78 plus 81 plus 79 yields us a 238. Divide that by 3 yields us a 79.3. Round to the next highest whole number, and our answer is 80. We will now look at our first course aggregate used in this blend, and we will be determining our GSB, our GSA, and our absorption values. Looking at the data supplied above, A is representing the weight of your oven dry sample. B is the weight of the surface saturated dry sample in air. C, weight of your SSD sample in water. So test number 1, we're going to look at our GSB, and it just says plugging in the values supplied on top of the screen. You just plug in the values to the simple equation. A divided by B minus C yields us a 2.768. Your apparent specific gravity, again, A divided by A minus C, which yields us a 2.840. The absorption, B minus A divided by A times 100 yields us a 0.9. So now we will look at test number 2. So test 2 on your GSB, A divided by B minus C yields us a 2.768. Apparent specific gravity, A divided by A minus C yields us a 2.837. The absorption, B minus A divided by A times 100 yields us a 0.9. Now we will average test 1 and test 2. You add those two values in test 1 and test 2, divide by 2. So our average for our bulk specific gravity of the number 8 is a 2.768. The average of the two tests for our apparent specific gravity is a 2.839, and our average for our absorption is 0.9. We will now look at our GSB calculation, our GSA calculation, and absorption calculation of our two fine aggregates used in this blend. The math is very, very similar to what we just covered in the coarse aggregate portion, but we have another value in these calculations that we're looking at. So looking at the data supplied, B will represent the weight of your flask filled with water to the calibration mark. S is going to be the weight of your saturated surface dry sample. C will represent the weight of the flask, sample, and water to the calibration mark. A will represent the weight of the oven dry sample. So on test number 1, we will calculate the dry bulk specific gravity, our GSB, using the value supplied above. It's going to be A divided by B plus S minus C, which will yield us a 2.755. For our apparent specific gravity, it's going to be A divided by B plus A minus C, which will yield us a 2.995. Our absorption, S minus A divided by A times 100, which will yield us a 2.9. Let's look at test number 2. Again, A divided by B plus S minus C, which will yield us a 2.756. On the apparent gravity, A divided by B plus A minus C, which will yield us a 2.993. in our absorption, S minus A divided by A times 100, which will yield us a 2.9. We will now average test 1 and 2 on our GSB, test 1 being a 2.755, test 2 2.756. Add those two, divide by 2, and our answer is 2.756. Your GSA 2.995, add that to 2.993, divide by 2, our average is a 2.994. In absorption, 2.9 and 2.9, the average is 2.9. Now we will look at our calculation on uncompacted void content of a fine aggregate, also known as fine aggregate angularity. So on the top portion of this worksheet, you will see the letter V and the letter G. V represents the volume of the measure. G represents our bulk specific gravity, our GSB that we determined earlier, which is a 2.755. If you move down to test number 1 portion of the worksheet, to your left, you will see the letter F, which represents the net mass of the aggregate, which is a 142.2. So we're just simply going to use those values provided to plug those numbers into the formula to the right on test 1. So let's look at test 1. We'll plug these values into the formula. V, which is your volume, 100.4. We're going to subtract that from F divided by G. F is our net mass of aggregate, 142.2. We're going to divide that into G, which is our GSB, a 2.755, which will yield us a 51.6. 100.4 minus 51.6 yields us a 48.8 divided into 100.4 times 100 gives us an answer of 48.6. So let's look at test number 2. Different values, same math. We're going to get our volume, which is V, 100.4. We're going to subtract that from F over G, which is your net mass of aggregate, 138.8. Divide that into our GSB of a 2.755. Will yield us a 50.4. So we'll subtract the 50.4 from our volume of 100.4, which would give us 50. 50 divided by our volume, 100.4 times 100, will yield us a 49.8. Now we will average these two values, the 48.6 and the 49.8. Add those two values, divide by 2, and as you can see at the very top of the page, our average would be a 49.2.